Welcome to the final session of Module 3. Previously we have discussed about the hardware architecture and the software architecture. So this is a continuation of the software architecture. Okay, like we have understood about the RTLab software. Now we'll be understanding about the how to make a MATLAB model compatible to real-time platform of OpenRT. So the outline of this presentation is basically the steps of performing this task. So as the outline goes by, so the first step is like grouping into subsystem. Okay, so the top level of the model will be having something like subsystems. Okay, then naming of the subsystem, then something called as adding the opcom blocks, then achieving the parallel execution. So the first step is grouping, then naming, then adding opcom, then achieving parallel execution. So these are the main basic steps of making a MATLAB model compatible to the real-time platform. Now, so this is what is the total architecture, like the hardware, the host PC, the target PC, the interlinking TCP/IP communication channel, then the MATLAB model, everything is shown in this figure. So we have understood to some extent about the hardware. Now let's go more into the software. As I told earlier, the first step is grouping into subsystem. So initially when we work with MATLAB, like variable step solver or fixed step solver doesn't matter. So we built a model. Okay, the top level of the model looks like this. Let us take this for an example. So the top level of the model is like only building blocks of the MATLAB model. Okay, like addition, subtraction, or talking about power system, like a transmission line or distribution line or any fault block. Okay, so the top level looks like this. Okay, but this top level is not accepted in RTLab environment. So we will be making them into certain groups of subsystem. Okay, so there will be like two subsystem basically here. Okay, so one will be the computation subsystem and the other will be the user interface subsystem. So the computation subsystem is basically comprises of all the computation parts of a model. For example, you are just working on PID tuning, okay, of a controller. So that is the computation part of a model. Okay, so that computation part will be in one subsystem. Then the results which are obtaining after the computation will be sent out to the user interface subsystem. Okay, now while computation, okay, when we are observing in real time, if you are willing to change the parameters on the fly during real time execution, we have to take the input from the user interface platform, because when we are executing the model in real time, right, so we are generating the C code of it and we are sending it to the target platform. So at that point, like the computation subsystem basically gets locked with the cores. Okay, so we'll not get direct access to it, but via the user interface subsystem we'll get the access to it. So we have to place those values which we are willing to change during real-time simulation in the user interface subsystem, but all the operations, all the computation will be done in the computation subsystem. Okay, so as you can see from this figure, so we'll be having a set of subsystem on this. Okay, so we'll be making all the computation into one subsystem and the user interface like the scopes, the display, or any constant values which you would like to change during real-time simulation inside the user interface subsystem. Now, so there will be two subsystems basically. One will be the computation subsystem, okay, and the other is the GUI subsystem. So this computation subsystem will be allocated to different CPU cores. Now, if you remember in the previous session I told you, like assigning target to subsystem, or like during building process also there was one step, finding the number of subsystem, computation of subsystems. So now like this computation subsystem can be multiple basically. Okay, the GUI subsystem is single. So the number of cores basically decides the number of computation subsystem. If you have one core activated, you will be using one computation subsystem. If you have multiple cores activated, you can have multiple computation subsystems. Okay, so that each computation subsystem can get locked to each core. Okay, and this GUI subsystem will be single for all these computation subsystem. So all the results, whichever value of whichever computation system you want to monitor during real-time execution, you will be placing in the GUI subsystem. Now, so the top level of the model should always be in subsystem and not as shown in the slide. So it will always be in the subsystem format. And yes, the GUI subsystem is not mandatory, but computation subsystem is mandatory. Why? Because, for example, I'll tell you, like most of the student researchers, okay, they are not interested in seeing simulink results. Okay, so why? Because when we are working with real-time platform, the simulink results are going to be exactly similar to the real-time results. Okay, so if you are monitoring your results during real-time execution on the simulink scope and monitoring the results on the offline mode, so both the results will be similar, but this will be a little bit faster because it is synchronized to the physical clock. So that is the only difference. Okay, so when researchers are working on a real-time platform, they are more interested in having a hardware interface. So they don't want to have a GUI platform. Okay, so they will directly connect this computation subsystem to the hardware. Okay, in that case, you don't need to have a GUI subsystem, just a computation subsystem. Okay, and how to interface hardware we'll be seeing in the next sessions. So as you understood, there will be like one computation and one GUI. Okay, let us just take the GUI also into consideration as of now. Okay, so we'll be having one computation subsystem and one GUI subsystem. Computation subsystem will comprise of all the mathematical operations, and GUI will only comprise of all the displays, results, or any parameter that we want to change during real-time execution. Okay, now you will be seeing some new blocks over here. I'll come back in the next slides to the about this. I'll be speaking about these blocks in the next slides. Okay, so distinguishing real-time subsystem and GUI subsystem. So the computation subsystem will be executed in the real time. Okay, uh, for accelerated simulation model on one CPU core of the real-time target. So what does it mean? So as I said, if you are having one computation subsystem, this will be locked to one computation core. Okay, if you have multiple subsystem, so multiple cores will be allocated at that instant, and the GUI subsystem will not be occupying any core. Okay, it will be running on your host PC. Why we are like separating like the displays scopes? Because we want to have access to those results during real-time execution, and when we want to have access, so where we will be accessing these values? On our host PC. There is no way to access the real-time platform if you don't have a host PC. So the GUI subsystem will be running on a host PC, and the computation subsystem will be running on the cores of the target PC, and they will be asynchronously communicate through the TCP IP communication. Okay, now assigning real-time subsystem to different CPU cores. Now for example, you have multiple cores. Okay, so you want to assign different tasks to each of the core. So you have to identify like which part of your model will be assigned to core 1 and which part of your model will be assigned to core 2. Okay, then you just have to make subsystems, then automatically these subsystems will be allocated to particular cores. So you don't have to manually do this, but there is an option to do this manually as well. If you want to do, you can do it. If you don't wish to do, you can avoid it. Okay, so you just have to make subsystem on the top level so that they can get automatically allocated. Now the first step was grouping into subsystem. Now naming the subsystem. So how naming affects? Okay, so the GUI subsystem is basically called as console. So we write it as SC in blocks underscore any name. You can place there any name you want. Okay, results, data, output, anything you want, you can give it. So SC underscore is compulsory for the GUI subsystem. So the GUI subsystem, it allows the interaction with the computation subsystem, runs on the PC asynchronously and not linked to any CPU core. And no signal generation, no mathematical operation, no physical model should be placed in the GUI subsystem. So the GUI subsystem is named in blocks SC underscore any name. Now coming to the computation subsystem, it will be named as two types basically. If you have single core activated, you can have something called as master. Okay, now if you have multiple core activated, then you can add something called as a slave. Okay, one core will be activated as a master and the other will be acting as a slave. Okay, so master is compulsory for all models because there has to be some computation part, and that computation part is called first instant is known as master. If you want to add more cores, then you have to add more slaves. Similarly, increasing the number of cores means your capability is increasing. You will be able to simulate larger models or complex models on your system. Okay, so this kind of concept is basically used in the real-time platform. If you remember the first session I told you, if you are fixing a time step for your model like 20 microsecond, and if you are getting an overrun, so this is one of the methods to actually avoid overruns. So if your model is quite complex and it is taking more time to compute, then what you can do, you can decouple the model into separate subsystem so that faster simulation can be achieved, because the model is getting smaller and it is assigned to particular cores so that faster simulation can be done, right? And with the same simulation time step, faster speed is achieved. So that is one of the methods to overcome overruns. So sm underscore any name is the master, ss underscore any name is the slave. Okay, so you can have multiple slaves, but there will be only one master and one console. So please remember this. So these are the various architectures you can actually have. Like one master, as I said, is compulsory because we need to have some computation. Then master or slave. Console is still not compulsory. If you want, you can have master console or master console slave. Okay. Now, so this is basically the different points. Okay, I have made into bullets. Okay, so that we can remember it easily. Only subsystems are allowed. SC underscore subsystem is the console or the graphical interface. SM and SS underscore subsystem are for computation. Then this one core is allocated for master and one core for slave. Then console subsystem will not occupy any cores. Okay, so this is basically a summary of what we have discussed till now. Now, adding opcom blocks. So the next step is adding opcom. First step was making subsystem, second was naming, third was adding opcom blocks. So what is opcom blocks? So basically to establish this communication between master and slave or master and console. So the communication between master and console is asynchronous, but since the communication between master and slave is happening between the cores which is on the processor chip, that is done synchronously. So there is no latency over there, right? So that is synchronous communication, but master and console will have asynchronous communication. Okay, so this opcom have particular operation for particular applications. If you are just having master slave, it will be applying the synchronous communication. If you are having master console, then it will be applying asynchronous communication. Okay, so the role of opcom changes with respect to the subsystem. So naming of the subsystem is very important. Unless you name the subsystem, please do not add the op communication block. So this op communication block will be found in the simulink library. So if you remember, I told you once you have installed RTLab, if you open MATLAB within it, then you will see all the libraries of RTLab getting installed in your simulink. Okay, so you open simulink library. If you search for RTLab, you will see the RTLab block in it. So once you just click on the RTLab block, you will see opcom block. Okay, so on the left hand side you can see the RTLab libraries like RTLab, RT events. These are certain libraries which we'll be discussing in future. Okay, so as of now we will be talking about opcom. So once you click on RTLab, you will see the opcom block. Okay, so you have to place this model after naming the subsystem, and this block has to be placed inside the subsystem. Okay, so this statement is very important. So as written here, all subsystem inputs must first go through the opcom block before any operation can be done on the signals they are associated with. That means whenever you are having a subsystem, for example console, one signal is coming as input to the console, that means that signal has to first pass via this opcom, then any operation will be done, like adding a scope or a display or any operation like addition, subtraction. Okay, similarly, if you place an opcom block inside a master or a slave, if any signal is coming as an input to the subsystem, that signal has to first pass via the opcom, then operation has to be performed with the signal. So naming is important. I'm regularly saying this, okay, continuously saying this, because the communication between master and console is asynchronous, master and slave is synchronous, again slave and console is asynchronous. So please name the subsystem, then place the opcom block. So opcom block has to be placed inside the subsystem and not outside the subsystem. So the opcom block must be inserted after after naming the subsystem. One opcom block can accept up to 25 signals in one subsystem. Okay, if you have more number of signals, more than 25, then you can add another opcom block. Okay, so each input can be a scalar or a vector. It depends upon your application. Now in the computation subsystem, okay, so one opcom is required to receive the real-time synchronized signals, okay, and one opcom is required for receiving the asynchronous signals. So this is one architecture which is very simple. Like we have only master and console. We are adding one console over here and one master here. So this console is taking two inputs, and the the opcom within the master is taking one input, right? Now, this is another example. Here we are establishing communication between the console and the master and console and the slave. So we are seeing one opcom blocks in each of the subsystem. Okay. Now, the next example, we are seeing like there is a communication between master and slave. The line is red because that is synchronous, and the blue line shows the asynchronous communication. Now, quickly going to the next slide. So, this slide basically shows two opcoms added in one subsystem. So if you can just try and analyze this figure, you will understand like the red lines are for synchronous communication, the blue lines are for asynchronous communication. Asynchronous communication is established between the GUI platform and the computation platform. Okay, so whenever there is a communication between the console and the master or console and the slave, then the blue lines are being shown. That means asynchronous communication is happening. The red lines basically shows the synchronous communication. So if you see the SM underscore computation subsystem, okay, there are two opcom blocks added. So one of the opcom blocks is receiving a blue signal and one of the opcom blocks is receiving a red signal. Okay, the blue signal is coming from the console and the red signal is coming from the slave. Okay, so if you open this subsystem and just check the tabs of the opcom block, you will see the difference. Okay, so the one of the subsystem receiving synchronized signals, okay, will have different number of values inside the opcom window, and the one receiving the asynchronous signal will have different number of tabs inside the opcom window. Okay, so the operation of opcom for asynchronous and synchronous communication is completely different. So please try to remember, do not use same opcom for receiving synchronous signal and asynchronous signal. If you are receiving synchronous and asynchronous signals into one particular subsystem, please make sure you are using multiple opcoms. But if you have only synchronous or only asynchronous signal, then please use a single opcom, because a single opcom can take 25 signals at a time. Now, the last step is maximizing parallel operation. Now, when you are having two computation subsystem like master or slave, okay, so how to achieve parallel execution? So what exactly is parallel execution? In layman's language, if I say parallel execution means starting like at the same time and stopping at the same time. Okay, the master and slave, they should start at the same time and they should stop at the same time. Like master should not wait for an input from the slave and the slave should not wait for an input from the master. So in that case, we need to understand something called as a state of the system. So what is a state? A state can be defined as an output which is computed only from the preceding inputs and outputs. Okay, and the state can be generated with the help of certain blocks in MATLAB environment by using memory blocks or integrator blocks. So if you see the example of the integrator block, it's written over there YZ, okay, that is the present output of the signal, is equals to YZ minus 1 plus XZ minus 1 into delta T. So YZ minus 1 is the previous output and XZ minus 1 is the previous input. So YZ basically depends upon the previous output and the previous input of the signal. Similarly, for the memory block, it is depending upon the previous input only. Okay, so these blocks will help us achieve parallel execution because they will not wait for the present input or present output. They are depending upon the previous values of the input and output. But sometimes people by mistake they add a gain block. Okay, if you see, the gain block basically depends upon the previous input. Okay, so please do not use a gain block to establish parallel execution. You have to use a memory block or an integrator block. So where it is used, I was telling, when we have two computation subsystem. You see, we have a master over here and a slave over here. So in this master, we have added one gain block at the sending end. Again, at the sending end inside the slave, we have added one gain. So now both of them are computing. Both of them are communicating with each other. One signal is going from master to slave. One signal is going from slave to master. Right. So if you are adding a gain block at these signals, these communicating signals, then there will be a deadlock happening between the two subsystems. Okay, why? Because these gain blocks will be waiting for a signal from the computation subsystem inside master. Again, the gain block placed inside slave subsystem will wait for a signal from the computation subsystem. So they will be keeping on waiting for each other instead of sending an output, and there will be a deadlock. none of the core will get activated. Now in this scenario, like the slave subsystem will wait for an input from the master, but the master will not wait for an input from the slave because an integrator is placed at the output of the slave subsystem. So it will send a value instead of waiting. Okay, so this will allow you to achieve parallel execution to some extent, but the best solution is having integrators or memory blocks at the output of the computation subsystem. So here none of the subsystem will wait for each other, they'll start simultaneously and they will stop simultaneously. So in this way you can achieve parallel execution. So the process of this session is basically shown in this outline. So please remember the steps: grouping, naming, adding, and achieving parallel execution. Right? Now, there are some basic guidelines we need to follow while working with real-time simulation. First, as I showed in the session 1, we have to use fixed step solver. Why? Because we need fixed samples, okay, for getting determinism in the output. But means this sample size can be bigger or smaller depending upon your application, okay. But if you are using variable step solver, what will happen, you will not get access to providing one single time step. So the solver will actually decide the time step for your model, and like the samples will not be of similar size. There will be irregularity between the sample size of the results. So there will not be any determinism in your model, so you will not be able to achieve real-time simulation. So now we understood how to achieve parallel simulation while using OpenRT platform. So next step is like configuration parameters in the MATLAB Simulink environment. But before that, I would like to remind you, like please remember the outline of the slides. Okay, the first step is like making subsystem. The next is like naming the subsystem, then adding op communication blocks, then achieving parallel execution. So these are the basic building blocks or like basic steps, foundation steps for achieving real-time simulation. So please remember them and then go ahead.